So let's look at how the electrical potential or the voltage compares to the Gibbs free energy and also that equilibrium constant. How is everything related? And so on your data sheet, you will be given two equations and you actually can put them together. So you're given this Gibbs free energy equation is equal to a negative n. That negative n, that's the number of moles of electrons transferred. F is known as Faraday's constant, and so it is given 9,600, 500 coulombs per mole of electrons. And then that E, that is your volts. The relationship between volts and coulombs is, and this is again will be on your data sheet, 1 volt equals 1 joule per 1 coulomb, or you could rearrange it and have 1 coulomb being equal to 1 joule per volt. And when you combine the two, you can, if you want to, combine it and get something that looks like this. This other equation, the negative R times the temperature times the natural log of K. So that K is your equilibrium constant. Remember, if it's above 1, then it's going to be a thermodynamically favorable process. It's going to make products. And that's one thing that you're going to see, that if your voltage is positive, you're going to have a K that's above 1. And then another thing you should know is that R, it's the R that has joules in it. So make sure that you pay attention. So it's the very first one that they give you. So the second and the third values of that gas law constant, it is for like Pivnert for your gas laws. But the very first R is for all this energy information. So here's another chart that combines them all. So again, we have a thermodynamically favorable if our Gibbs free energy is negative, if our K is above 1, so meaning that we have more products, and if our electrical cell potential is positive. It's not favorable if we have all the opposite. So, and especially if we have a negative electrical cell potential, that means we're not producing any voltage. Now, if we're at equilibrium, remember that Gibbs free energy would be 0, and my electrical cell potential would also be 0. And we call that a dead battery because we have nothing going back and forth. The not favorable line, we could get that cell to occur if we gave electricity to run it, but just the way it's written or the way it's set up, it would not happen. So again, you can split these equations up. You actually can combine them to get something like this. And remember, this little knot right here, this means standard conditions. So let's go ahead and do a problem while we incorporate some of the things that we did from the previous unit. And now we're going to add our Gibbs free energy value. So first of all, it says write a balanced equation when copper takes electrons away from aluminum. So let me look at my electrical cell potential chart just to help me out and to look up the voltage. So it said that copper takes electrons from aluminum. So that means my copper is my reduction half step. That means aluminum would be my oxidation half step. So this is the one that I reversed. And I already changed the sign. So the sign was a negative and I changed it to a positive. As far as writing a balanced reaction, I need to make sure I cancel my electrons. So I am going to have to multiply the top one by 3 and the bottom one by 2. And then I'll get 6 electrons for each one of those. Because I have 2 electrons in the first one and 3 in the second one. So I have to do a common multiple of 6. So when I add that up, I get this reaction with my 6 electrons being lost and gained. Let's go ahead and find our electrical cell potential, so what E is. And I just add those up because again I already reversed the aluminum sign, and I get my volts as 2 volts. So now that I know what E is, then I can use this equation to find out what my Gibbs free energy is. So I do need to put in my N. So that's why it's important to look at that equation and figure out how many electrons are exchanged, because I do have 6 electrons that are exchanged. And then for my Faraday constant, I have 96,500 coulombs per 1 mole of electrons. And then my E is in volts. And so to cancel out units between coulombs and volts, I'm going to use this, and it's joules per volt per coulomb. And that is from the data sheet. And then I put in my volts, so 2 volts. And so you're going to see that everything will cancel. So I get my volts canceling, my coulombs canceling, my moles canceling, and I should have wrote moles of electrons here. And so then my units is going to be in joules. And multiplying this out, because I am joules, I typically going to get a really large number, and I get over 1,000,000 joules. So to convert that to kilojoules, and it doesn't say to have it in kilojoules, so I could be finished. But just dividing by 1,000, I'm going to get a 1,158 kilojoules. And one thing I did forget that I'm looking over, this is negative. So my delta G is negative, and so we know that it will be thermodynamically favored. And that's one thing that I seem to do, is to drop that little negative. So watch out for that. Don't be like me. So if you get a positive volt, you will get a negative delta G. So that is just goes with the territory. Now let's go ahead and find our K. So I'm going to use this other equation here, and I will use that R, and against the first one, the one that has the energy unit, the joules. So let's go ahead and solve for that. So I get delta G equals the negative, so don't forget that, and then times the temperature. And I actually do know what the delta G is, so I'm going to go ahead and replace that here on this line. And I am going to use it in joules just so that my units match. So that's the biggest advice that I can give you, is make sure you write out all your units so that everything is matching and you can see how everything cancels out. So go ahead and do this math, and I end up with my natural log of K as equal to 467.4. And then to remember, to get it out of the natural log, you are going to raise this as an exponent of E. And when I do this, I get a really large number. And that is because I am forming products. So my K is really, really large. I know I'm going to form products. So notice that these three values go together. So I have a positive volts goes together with my negative delta G and with a really large K. So those three things will go together. But this is how you go from one to the other. So if they give you the equilibrium constant and you find it, and then you have to find the volts, then you can use that, use these equations to help you find the volts.